Wait a bit.
Well, good afternoon, PCS members and friends. Today we have a seminar by Dr. Ivan Khaymovich, and our scientific host today is Aditya. And please let you introduce the speaker.
Thank you, Oleg. It's our pleasure to have Professor Ivan Khaymovich from the Nordic Institute of Theoretical Physics, Nordica, here with us and presenting this seminar today. So a little about Professor Khaymovich. He did his PhD, defended his PhD in 2013 at the Institute for Physics of Microstructures in Nizhny Novgorod. I hope I'm pronouncing this correctly, in Russia. After which he was a postdoc at Aalto University in Finland. And then in 2015, he joined as a postdoc in Grenoble, France. And I will not try to pronounce the name of this place. My French is terrible. But following which he was after the talk. After the talk, yeah. From 2016 onwards till 2022, he was a staff scientist at the Max Planck Institute for the Physics of Complex Systems in Dresden. And from 2022 onwards, he's assistant professor in the theoretical quantum matter group in Nordica in Stockholm. So, and today he will tell us about effects of correlations in disorder on localization and other phenomena. And welcome, Ivan, and over to you.
Let us welcome the speaker.
Too early. Soon after the talk is better.
Patience.
Yeah, okay. Thank you very much for inviting me here and for having me here as a speaker as well. So today I would like to speak about models which are usually long range, but single particle and they are disordered. And what I would like to focus on is what are the effects of correlations. For example, if I consider like a system like that is like this is the diagonal, just this is the matrix which I show, and I change the correlations from completely uncorrelated to fully correlated, I will change the phase diagram. Even without changing the disorder amplitude, I can undergo the transition from ergodic metallic behavior to the localized one, just by changing correlations. Or vice versa, I can consider even, I will tell you what does it mean, the systems which are self-dual with respect to the Fourier transform, which are not given by quasiperiodicity. And here, for example, you have spectral statistics and you see like two parameters, disorder and correlations, they are related to each other, and this diagram is symmetric with respect to the bisector, while the spatial so in space structure of the wave function is different, and this showing that in the real space basis, it's like that. If I would like to consider the same diagram in the momental space basis, it will be just mirrored with bisector. But before we go there, let me just give you a flavor of what I'm doing and why it's interesting for me. What I'm doing can be characterized by the two words ergodicity-breaking. And in order to understand what is ergodicity, what is the meaning of this ergodicity, let me just tell you first what is ergodicity. In classical systems that we're speaking about ergodicity, what is this? It's generalization. I just take some non-equilibrium system, for example, a glass of water, put the ice, isolate the system and wait. What do we expect? We expect that the system will generalize, right? So this is the way how it usually works for chaotic systems, classical situation. But like, and this is like the distribution which we started with. The distribution we end up with is just a Gibbs distribution. This is called generalization. This is given by chaos in nonlinear classical systems. But if we're speaking about quantum systems, it's not always true, and sometimes we see non-ergodicity. What does it mean in terms of the same picture? I prepare the same, I do the same as the system, I wait, but it doesn't go to the same external state. Instead, it goes to some other non-equilibrium state. It can be the same, it can be different, but it's surely not equal. And this is called ergodicity-breaking. This is more or less like the basic feature. What I'm interested in, I'm interested in quantum systems under disorder conditions. I just add some disorder, and I will show you some funny pictures about that. If we're speaking about clean systems, then the particle can go from one corner of the sample to another. If it's fully disordered, then this particle is really stuck. And this is the disorder potential, you see. It's impossible, like this particle is localized in one corner of the system. What I'm interested in is something in between. You have some disorder, but the particle still can move, but maybe this movement is only allowed in the extensive number size, but measuring 0 for sample. In this sense, this left one is called ergodic metal. In the quantum, in condensed matter physics, this is an Anderson insulator, many-point insulator, if we're speaking about interacting systems. And this is a non-ergodic extended phase. So extended because the number of configurations where the particle can live extensive. In terms of the volume, it's not localized, but it's still non-ergodic because the particle cannot really observe the entire system, and even by the particle. So in this sense, ergodicity is here, but not here.
So, yeah, how is this different from mixing?
It's not
Linear. So mixing is classical, but we can define mixing for quantum systems also, right?
Yes. We can define it for linear systems, not only quantum but classical as well. But the question will be, okay, so here, so you are saying that this is mixing and this is not.
What is the quantum definition of mixing?
As local observable will spread.
Well, he didn't even talk about mixing. He talked
Yeah.
about ergodicity. So maybe we want to first listen to your quantum
Yeah. Okay, let's
definition of ergodicity.
Okay,
No, but
sure.
will you say something about that at least?
Yeah. So
Because you said in a few words what you mean by classical ergodicity. So what is then quantum ergodicity?
Quantum ergodicity is just single system realization. I will not go into the details. So just definition of this quantum ergodicity for me will be just I consider local observable if it thermalizes, all the fluctuations are small, not only small but scale down with the Hilbert-space dimension as one as well.
And local means in what space?
Local is in my laboratory space.
Whatever that is. Right?
Yeah, whatever the disorder is where it's local, right? So because it's also in some space. Because I can put non-local disorder, then. So in terms of the states, what I again the same basis where the disorder is local. I will see the states here, like it's many body or single particle states wave function density, which will be spread over the entire volume. Here it will be localized on a few sites, and here it will live on the fractals on multi-fractals. These are the states of my interest. So in terms of the systems which I'm working on, I start with random matrix theory. So random matrices are random matrix theory is the framework where you can forget about system specifics. You can just say, oh, I consider just symmetries, a topology of the system, map any of the system to the random matrix one, and just consider what will be the phenomenon there. And qualitatively, I should see the same phenomenon in the same transition. If we're going beyond this universality, if you want, I'm working on long-range systems, and here I should mention dipolar systems mostly. For example, you can keep in mind many dipoles. Some of them are excited and only dilute ones. And if I put them, say, in the electric field and the disorder potential, at the same time, this electric field will put some correlations on the dipole orientations. And the direction of the electric field will change this correlation between dipoles. This is one of the examples. But this is what we will speak about today in the most exciting level. If we increase,
why there is this either random matrix or long-range system? Cannot you have random matrix with long-range
of
correlations?
course you can.
So
Of course
it's,
you can. Of course
it's
you can.
not a strict.
No, it's not a strict definition. It's just three states like this is. This doesn't have the direct experimental feasible setups. So you can ask Barbara about some random matrix realizations of random matrices. It's not very easy. This one has immediate applications to ultra-cold atoms, a few excitations or to localization of light setup, many of really experimentally feasible ones directly. And the third one, if I increase number of excitations here, I will go to the many body systems, and there all these questions of ergodicity-breaking are bumping up with the phenomena like many body localization, Hilbert-space multifractality, all this stuff. Today we will focus on this part and a little bit on this part. So just to give you a flavor of the research areas at glance, more or less as I mentioned here, these three research areas. So then just a few examples. In random matrix theory, in 2015, we just described the first model where we found not only localized, Anderson localized and ergodic phase, but this fractal one, which was Rosenzweig-Porter, and now many people are working on that. Then in these long-range correlated systems, this is what I will speak about today. We found that correlations can really move your transitions, like really push your system from the ergodic phase to the localized one. Correlations can be given by electric field to its orientation. In many body setups, you can do many things, deviation from the page weight, the entanglements, dynamics, real space and Hilbert-space picture of many body systems, and even relation between entanglements, multifractality, all this kind of stuff. You see a lot of that. If you're interested, you can just scan this QR code and look at this website. But we will focus on this small corner because like, otherwise we don't have time. So here I just mentioned several words on this topic, and you see it's like it was a small corner, but many people are involved, and I will focus only on two papers. The first one, which we did with Kravtsov and Nosov, and the second and the last one, more or less, which we did with Shilpiro and Sarapasu. Okay, eventually after all this introduction to the introduction, this is the outline. What I would like to speak about, first of all, I will introduce, because I will need this, what is Anderson localization transition and why we don't have it as a transition in 1D and 2D in the standard model, how to restore Anderson localization as a transition in different setups in low dimensions in 1 and 2, either with correlated disorder or with long-range hopping, and like we will understand how to really count resonances there. So as an example, I will take this well-known power law of random quadrant matrices. And after that, I will give you the puzzle, which was first found numerically, and then we understood it analytically. And resolution of this puzzle, analytical resolution, just to give you the flavor of it. Some of these parts will be more technical because you can generalize it. And in the last part, I will focus on this recent paper where we considered correlations not in terms of the kinetic term, but in terms of the dynamic. Let me start from the very beginning, from the introduction. So please stop me if you have any questions on the. So what we're speaking about, if we have Anderson localization, it's just the usual time-binding model on certain lattice. You have uncorrelated random disorder. You have hopping, which is nearest neighbor. And then if you are in high enough dimension, larger than 2, then what you see is that it's this particle living in the disordered potential can hop and can be described as a classical particle just going through the scattering. As soon as this works, as soon as the mean level space, mean free path is much larger than the first one. If we increase amplitude to the disorder, so we undergo from here to here in large enough dimensions, it's not enough even to have large dimension. So we should take into account the interference. So for example, if we would like to calculate the probability to go from this site I to site F, we should first sum amplitudes of the trajectories and then take the absolute value in square. It's not only taking the probabilities, which are squared amplitudes, but also contains the cross terms, interference terms. For example, these pairs of trajectories, whether I'm going to the same set of impurities, either clockwise or counterclockwise, they will give me the same amplitude with the same phase. And therefore, these kind of pairs will use the scattering back localization. Within these two, we have Anderson transition. And below the critical disorder, we have the states, at least some fraction, finite fraction of them, which are metallic, ergodic. Above, we have correction without opening the gap. So it's not the usual banding split, just Anderson. The question which people asked already in 70s, or like even Anderson himself in 50s and the 50s. Okay, so if we start with this picture of through the conductivity, we add this interference corrections, quantum corrections of weak localization. if we do it in low dimensions, the corrections will blow up with the system size, either linearly or logarithmically. Which means that in the thermodynamic limit, what we see in this model is that everything is localized for any finite disorder is 1D and 2D. And the transition, what we have is just in 3D. But look at our laptops, look at our phones. We still see wires with which are metallic, which are not all localized. We see conducting planes. What is going on? Something is missing. So even if I forget about like opening of the system, which I will not consider today, like electronic system is coupled to phononic ones and all other modes, environment. Even beyond that, what we have in principle, we can have the delocalized regime in low dimensions if we take into account one of two elements. Either we cannot consider this disorder to be uncorrelated, or we can take correlated one. If this disorder is correlated enough, then we can delocalize the system even in 1D. Or because of the coupling to the environment somehow, my copying is not nearest neighbor, it can be long range. Okay, let me just focus. Mostly I will focus on this long range in my talk, but let me first consider this correlated. One example. If I affect disorder, let me just consider the model suggested by Aubry-André in 1980s. And there they just replace randomness by the potential, which is cosinusoidal, but with a rational number. It's like you are looking at the following situation. This hopping is given by the potential, which is very deep. On top of that, you just add small potential with the period incommensurate. What we know about this model, it has a transition in 1D. And the transition happens at W equal to the amplitude. How to understand that is very simple. If I take this Hamiltonian and just go to the momentum space, then immediately everything which was on the diagonal, because it's correlated in cosine, will be hopping term. Everything which was just hopping term, which was translation invariant, will be just diagonal term, which is cosine. And you see immediately that, so I just, in the momentum space, exchanged parameters J and W, apart from that, they are the same, two Hamiltonians which are the same. It's self-duality. Of course, I trick you a little bit because I consider not the usual discrete Fourier transform, but Fourier transform with this incommensurate period. But you know, it's possible to avoid having this, still have the same. Just a question of the order. But what we see immediately that as soon as I'm localized in real space, immediately after the Fourier transform, it should be delocalization in momentum space immediately, because it's just Heisenberg principle, if you want, of the Fourier. And vice versa, localization in the momentum space will correspond to the delocalization in real space. And this point is the self-dual point where W and J are the same, and these two Hamiltonians are the same in real momentum space. It cannot be neither localized nor metallic. I wouldn't say according. And this is multifact. Simple. Correlations can move my transition from 0 to finite value, even in 1. Another way, how can I do it? I will affect the hopping term, kinetic term. So the idea here is the following. So all of you know that if I consider dipole-dipole interaction, it decays in the power law fashion. So of two dipoles, right, of the distance. And if, let me consider the system of dipoles where only few dipoles are excited with this blue hand. If I apply this interaction term to this system, what we immediately see that it will just flip to dipoles, right? And it looks like my excitation just propagates over a certain large distance with the amplitude decay. If I have dilute number of excitations, I can describe it with a single part Hamiltonian where the hopping term is decaying in this power fashion. This was considered in the 80s, and it was found that indeed, in this situation, you can have the transition, but not as a function of this amplitude of the disorder, but as a function of this power. How can I change the power? What is this power 3 in three-dimensional system? What I'm doing when I'm applying this dipole-dipole interaction, I'm just exciting the photon in the free space by dipole switch, and another dipole just absorbs this. And this 1 over r cubed is just the propagation propagated the light. Now, if I change something, for example, I will put it in a cavity, or I will consider not only light as the source of this interaction, I can change it. And this is what people consider. Well, in the next couple of slides, my main parameter will be this power. And I will explain you why it's not. What I would like to consider, I would like to simplify even for a moment this guy.
So just to understand, so you have this power, this long range hopping, if you wish, yeah, and you still have this order.
Yes, and I have this order which is uncorrelated.
Uncorrelated.
Yeah, so I forgot about all these correlated ones, so it's a different scenario. Uncorrelated disorder and this hopping, which
One question about the notation. So you write in this Midland and Fyodorov paper, you write it as an expectation value.
Yeah.
So there is disorder there as well.
Yeah. So this is what I would like to tell you now, because like at that time people said that, oh, if the orientation of dipoles are really random, let me replace this complicated dipole numerator just by the random Gaussian. And at that time, it showed the same picture as I will show you today. If they are not oriented in the random directions, it's not guaranteed that the phase diagram is the same.
So the upper equation comes from the coupling of the dipole with the 3D photon.
Yeah.
And this thing, the next one comes from the couple of the dipole with the cavity.
With some mode, yes. Or maybe with multi-modes, because with one mode it will be all-to-all coupling. And in this
Can
sense,
you briefly explain how this small a come out from the cavity?
yeah, so I need to have multi-mode cavity and the modes which should survive in this cavity, they should have the corresponding profile, decay in space. It's not the best cavity, therefore it's not really just sinusoidal. I should do it in the more convoluted.
So alpha bigger than 3. So now this is small a bigger than 3. This small a, the small a
is
bigger than 3.
no. So what people can do in different systems, they can change it from 2 to 6. If we're speaking about not this setup, but for example, trap lines, it will be 1 for the direction. But around 1, I don't know whether it's possible to change. I know that from 2 to 6, it's possible. So it means that in 3D, for example, I can go below dimensionality and
So you like changing continuously this parameter?
as far as I know, yes. Not around 1. Around 1, I just.
How the wavelength of this photon compare with the
No idea. I don't know how it's in practice. So let me just try to describe this one. Like for a moment, what we did, we just consider this A as a control parameter, this numerator will be random if I consider the mean value, or if you want variance, it's not very important. And I would like to consider what will happen with their potential. Like potential is just random, and hopping is long range. What is known as oops. So quick. So what is known about these models from the 90s is that the transition is happening as a function of A, and it's happening at a certain point which is corresponds to the dimensionality of the system. Let me just try to give you the flavor why it is so. Let me first send my A to infinity. If I send my A to infinity, you see that n minus n cannot be larger than 1. It will be just time by 1 near stable hopping. I return back to the d-dimensional Anderson model. Everything should be localized. If I go to A going to 0, then it will be all-to-all coupling. It will be just Gaussian random matrix ensemble. Everything is recorded. Something in between should happen, and I will try to tell you what is happening. A. For this, let me just consider the perturbation theory in terms of the pointer. Let me consider that I'm somewhere at large A, so it's really short range, but still it's all-to-all coupling, but just with the amplitude decays.
Sorry, just a clarification question. So this mod of m minus m, this is kept fixed. In your model or
It's
not?
just the difference, the distance between two slides.
So it can be anything.
Can be whatever. What do you mean fixed? It's like it's between n and n. I can jump between all of them.
No,
Just m.
I was just saying, maybe, I was just thinking like in type binding model, we go from m to m plus one to
Yes,
minus one.
this will
and-
be a limit of a going to
Yeah. Okay,
a to infinity will give you exactly that, because as soon as m minus n is larger than one, if you raise it to any power, like with to infinite power, it will be.
okay.
Is it crucial that you assume that J is random, or you can assume that it's just a constant? In what is
We'll
now?
see. For a moment, it's random.
The one is random.
Yes. It will change in a second. I will show you. It's exactly the point of this talk. Half-one. So, but let's consider like this, just a perturbation theory. And if J is small, like A is large enough, it means that J is rather short range. What I expect to see is that perturbation theory will work somewhere here. Why I expect this to work is the following. If I consider the random potential, then the main problem with this perturbation theory will be that at some long distance, it happens to be that I have two levels very close to each other. Closer than the amplitude of the hopping. And therefore, this term will be larger than one. It will be resonance. I cannot use usual perturbation theory. I should use degenerate perturbation theory. Now, what is the problem? Like I should hybridize them. If the number of resonances let me fix, for example, one point where I started with, and then the question is, okay, how many resonances do I have in a certain distance? If this number doesn't grow with this distance, just finite number, that's fine. I just hybridize several of them after the perturbation theory. But if this number will grow with the system size, with the distance, will be one. Okay. So then what I should do is I should find the typical distance between adjacent levels at a certain distance r, which is m minus n. How can I do this? So what I know about these diagonal levels, they all are just random in the certain interval w, independent. And if I take the distance r, immediately what I have, so how many such sides do I have in the radius r around my point in d-dimensional space? Just r2d. So it means that the typical level spacing between two adjacent levels will be this energy window divided by number of them, r2d. Decays in the power of fission. And this also decays in the power of fission. I should compare this to it. Right? So if A is larger than D, what I have, even if W is very small, after some distance, finite distance, this decays faster than this one, this J will be smaller than energy difference. At some finite distance, I have a lot of resonances, but finite number. After this distance, after maybe hundreds, thousands of resonances, I have nothing. I have just localization. If vice versa,
And the localization is now algebraic, or
yes,
it is,
of course, because perturbation theory will.
And do you see maybe also intermediate exponential localization with a crossover into algebraic at some critical distance?
It depends. Yeah, it depends on the model, but sometimes yes.
See this.
And what will happen if my A is smaller than D? It doesn't matter how large is amplitude of the disorder. This decays slower than this one. Time to distance, more and more resonances. Right, the number of resonances scales as JR to this energy difference, and it's up as soon as K is. So what we know from this? For sure that this is localization because perturbation theory is divergent. And this shows us, oh, perturbation theory diverges because of number of resonances. So what people concluded in the 90s, it should be transition, and transition will be at A equal to D. And this worked. Yeah, maybe we can skip this multifractal states, or like, do you know what are multifractal states? Please raise hands who doesn't know.
Let's say Jude.
Yes.
You would like to, okay. So let's do this. Okay, let's go through this.
No, what was the question? Who knows or who doesn't? No, that I know.
So if you know that,
Everyone knows.
Everyone knows what the multifractal is. Okay, fine, great. You should know. So if you have any questions about that,
So what's the case that A equal to D, then does it depend like,
it's multifractal.
yeah, but
It will depend on the other parameters than irrelevant for localized situation. But let me avoid focusing on the critical point for a moment. Let's consider just phasing, because even here we will find very peculiar things in the next two slides. Just to summarize, indeed, as Sergey mentioned, it's a power law localization. If I plot the logarithm of wave function and the logarithm of the distance, it will be power law. And this power will be just given by this. Sorry, sometimes it will be alpha, sometimes it's a. It's the same. Will be the same as this a or alpha as soon as we consider this amplitude to be random. Returning back to the comment of Buddha is the following. Okay, let me just play around and change this random number. Like this is showing that this scattered part by the constant.
By a constant.
Yeah.
So the hopping is
Constant, decaying.
Algebraically, but is a constant.
Yeah, it can be random single number, but it's not important whether it's random or single number.
No, alpha is 3.
No,
No.
no critical alpha whatsoever. Everything is localized. In the bulk, everything is localized. It's a surprise. So at least numerically, it was a surprise in 2016, 2018. And moreover, the surprise was that, okay, on the right-hand side, doesn't matter, just perturbation theory. What are the correlations here? It's not important. It's still power localization with the power A or alpha here. What was seen here is that the localization in the bulk here is the localization with the power symmetric with respect to the point A equal to D. It's 2D minus alpha. So here it's not a surprise. I increase A, I make my system more and more short range. My wave function is correspondingly more and more short range. Here, if I go here from this point, I make my system more and more long range, but instead, my wave functions are more and more short range, localized.
But it should depend on how random J is, right? It cannot be because
This J is constant.
J is constant.
This is the point. Like in the previous situation, if J was the random matrix, it was ergodic.
So what if I make J very tiny random? So if the disorder in J is extremely small, what will happen?
Extremely small means scaling by the system size or just small finite?
Just anything small.
Small.
You return back here. You return back here.
So there's some length scale on which I will see that.
Yeah.
So my wave functions seem to be localized.
So a follow-up to that question. So instead of taking a small disorder, if I take it as a much more constrained disorder, as let's say just plus minus signs, randomly choosing plus minus.
Randomly choose. Doesn't
Yes.
matter, it's working.
It will be always.
If you consider a randomly staggered potential thing,
Yeah.
it will be that one because staggered potential is just rank 1 perturbation. I can take it out of the phase for the wave function. If it's not,
I see.
This claim is true for any dimension.
this claim is true for low dimensions, small or equivalent to. Otherwise, it will be like, otherwise here, I will have the mobility. So the first paper, and the same year as Lebedev, Fourier did with his supervisor Maximov, they considered 3 dimensions. They found instead of multifractality, at the critical point, they found the mobility. Later we discussed with him that here is going to be still what? Mobility in 3D. So still localized states. Okay, this is the puzzle. How to really understand it? Because here the perturbation theory diverges. What can we do with it?
So yes, another question. So this form of the wave function, this is perturbation theory argument or just numerical?
No, this is just numerical observation. So this is the numerical observation of this paper.
Thanks.
You know, this therefore. Okay, how it's possible? So first of all, yeah.
Is it like, so is the thrust of the argument is that if you do that, if you make J being a constant, then it becomes integrable throughout somehow?
The integrable point is alpha equal to 0. It's Richardson's model. Apart from that, it's not.
I see.
I mean, it's not better than that's integrable. This is.
Okay.
Okay, so what we know about the system? First, of course, we know everything for A larger than D, because it's just perturbation theory and it doesn't matter what are the correlations, it's first order perturbation theory which will work. what we know. What else would we know is like for A smaller than D, what you see is like, forget about diagonal disorder. This system without this diagonal disorder is translation-invariant. I can go to the momental space basis, like in Aubry-André. If I go to the momental space basis, this will be just diagonal production. And this, as the disorder was whatever disorder only diagonal to the translation-invariant. If I do this, so this term will be diagonal, this term will be, this diagonal term will be just the hopping. This was Gaussian, this will be Gaussian, which scales down the square root of the sample volume.
What about the fact that if you take this J alone and you transform and you compute the dispersion relation,
Indeed, this is what I would like.
then you get non-analytical functions. And how is that affecting this duality point?
Indeed, this is what we are doing. What we will do in the next couple. Indeed. So what Sergei is saying is the following: A is smaller than D. What we are doing, we're doing Fourier transform. Let me focus on not on the Fourier transform, but on the zero momentum. Just a series, the sum of these positive terms, which decays the power law with the power smaller than dimensionality, the sum. It's diverging immediately. And it works also for finite small momenta. The spectrum will diverge. It will be non-analytical. It means that I can do the same, I can play the same game as the real space. I can say, oh, the level spacing here is huge. With respect to the hopping term, which is 1 over square root of the volume, I can find the threshold until which small momenta or large energies where the states are localized in the momentum.
But non-analyticity stays also for larger A, just in higher derivatives of the version equation. Right?
Yeah. So we can discuss more details of how it works. Like, let me consider a large enough disorder where, like for A larger than D, it's not important they will be localized. For small disorder, indeed, it will be also interesting to consider phenomenological weakness. Maybe you remember 2018 Solomon. Okay. In any case, so in this situation, A smaller than D, we have extensive number of states which are localized in the momental space, which means that they are nearly plane waves in the real space. They are dealing with. If I count the number of them, it will be measure zero at really high energies. What will happen with the bulk of the states, which are measure one? This is the question. How they will be affected by these states of high energy, which are nearly plane waves. What we know about this? So if we write down the Hamiltonian in these two terms, diagonal real space term, which will be hopping in momentum space, and this hopping term, which will be with divergent spectrum at small momenta, we see immediately that some terms, they dominate this hopping because the energies, they are very, very, right? And also what I can do, I can say that in the momental space, I can just write down perturbation theory for these states. Let me just rewrite this hopping term in terms of these new wave functions, not in terms of plane waves, but in terms of nearly plane waves. And I will just consider this P smaller than P star states will be perturbative, and the rest will be just something which is not divergent with. If I do this, immediately my hopping term will be these terms, which are projectors on the eigenstates of the whole Hamiltonian, with energies which are huge and something which is small. What will happen if I act by this hopping term on other bulk eigenstates of the entire Hamiltonian? They should be orthogonal to these states. They will see only this residual part. They will screen out from the kinetic. So this measure zero states, high energy states, will screen out really huge part of the hopping term of the rest. And this is more or less the take-home message of this part. After that, I will just show you how to find this residual part and how to show that it's really this power 2d minus a, not a. But this is the main take-home message. If you can see that, oh, my hopping term is divergent, the spectrum is divergent, and these states are really plane waves or nearly plane waves, you can really see that it might be the case that the bulk states are localized, even beyond their convergence of the population. Okay. So in this sense, it's not directly related to correlations, it's more related to the spectral properties. But what can we do? So let me first do the following. So what is here, like this orange line is just zero value, and therefore some of the energies are below zero, some of the energies are above zero. And the point is, if I would like to get rid of these high energy terms, I cannot just project. It's not enough to find what will be the effective model. What I would like to do, I would like to diminish them, for example, by sending to the denominator. How can I do this? I can add the constant term to this model. What I did here is just the eigenproblem. So eigenproblem, where a diagonal part on the right-hand side, hoping term, which is diagonal momentum space on the left-hand side. I add the constant diagonal matrix in such a way to make all the eigenvalues of this matrix to be positive or negative. And here is the diagonal, and invert this matrix. As soon as I invert this matrix, immediately all the large terms will become small ones. All the terms of order of 1 0. So it means that I can rewrite the same eigenproblem in the problem which is written in the convoluted, complicated way, but nothing is given by high energy terms. So this term is diagonal, and this term narrow scatter. Instead of this divergent one, I have something which is similar but good. So, but at this point, you should stop me and say, oh, what you did, it's like now I cannot solve this equation because the unknown eigenvalue is convoluted with the matrix, which is full. How can I solve it? Don't worry, we will solve it in the perturbation tube. So how can I do it? I will just use the properties of matrix M, because translation invariant in real space it will be. You see, translation invariant, each diagonal is has the same values. And therefore I can separate, for example, the main diagonal value from the rest. Main diagonal value will be here. So these are the terms which are all diagonal. These are the terms which are diagonal. And what we see here, this is the effective energy, eigenvalue, which I don't note it. And this is my effective copy. What is here? Like this guy is of order of 1, energy is of order of 1 if I'm sitting in the bulk, not at the edge state. No singularity. And this is the matrix which has the limited bounds. Let me just calculate what will be the decay rate of this guy. For the momentum, for this power law decay, in term with A smaller than D, what I'm doing, first I'm just taking the Fourier transform.
It's working.
Okay, that's just stuff. So if I do the Fourier transform of the power law, it will be power law. It will be the size of the system divided by P to the power D minus alpha, right? What I'm doing next, I'm inverting the Hoping term. Instead of these energies, I have 1 over energy. Therefore, I'm changing D minus A to A minus D, and then it's again power law I'm doing the inverse Fourier. And you see, like if I change here A minus D by D minus A, you see that the power will be 2D minus A. 2D minus A, it's exactly the power which we saw here. For the bulk of the states, we should have this localization because of screening, respectively. Then you can ask all these questions, which again, Buddha asked, okay, so how important is that it's correlated? Is it possible to change this? The main feature is this. If still the spectrum is singular, it's fine. If with small amount of disorder, you will destroy this feature, that's it. So what can you do, for example, like what I mentioned with this two-dimensional plane and effective electric field, I can do the same if my electric field is perpendicular to the plane, I will have exactly this. If I tilt my electric field, just dipole-dipole interaction, then what I will see that this will change and one peak will go not to the one peak will go up, another one will go down. And at some point, as soon as I see that I have divergence in both directions, I cannot find this constant to do this inversion. It will give up twice. Just as a function of the tilt value. Just here as a function of all these conditions. And yeah, here I already mentioned that, so this will work from certain distances, this decay. And also it works for all like measure one of the states up to the dimensionality after the states. What can we do else with this? So not only anisotropy with respect to electric field, we can ask the following question. This is what say yesterday. What about Euclidean matrices? What are they?
So can I ask
Sure.
a question? So because you are putting this Richardson model with this Burin-Maximov model, does it mean that the localization property in both these models are the same, or is there a
They're related,
difference?
but no, unfortunately, because Richardson's model is the integral point,
Yeah.
there is the jump. Like if I consider the limit of a going to 0
Mhm.
and a equal to 0, the localization, if I consider a going to 0, you see, like, let's consider one dimension.
Mhm.
Then the wave function, not the wave function intensity, but wave function decays the second power.
Okay.
In Richardson's model, it will decay as the first power. It's a jump because it's integrability. So it's not continuous as soon as if you consider alpha equal to 0 or alpha equal to 0.
I see.
In this sense, integrability points doesn't show you this.
Okay.
This like at least this is one of the hints why this is not.
Oh, why this is not?
This is not integrable. Like it's a
Yeah,
jump. You see, it's like it's not continuous.
So this, I mean, so there is this distance n naught at which you see asymptotic conversion, so to say, to power over decay. And how is this n naught depending on?
Numerically, it depends on the amplitude of the disorder, and it doesn't depend on the system size.
Energy?
It depends on energy. Of course, if you go closer and closer to this space, it will diverge.
I think here.
Yeah, maybe another question which can be asked: what will happen? Like a larger than d, do we have still these states? It was also your question. We still have them, but it's not a divergence. It will be just the finite, like big but finite energy. As soon as my disorder is larger than its energy, all of them. If it's smaller, then I have still measured zero states, which are delocalized up to a equal to 3d. Okay, so what about the Euclidean matrices? What are they? So what we considered so far was something like that. So we are living on the lattice. We have diagonal disorder potential, and we have this smooth function of the distance, which is there. Like we consider power law, but in general, it can be any smooth function which decays slowly. Logarithmic. What are the Euclidean matrices instead? Instead of having any potential, no potential is there. All of their sides are the same energy, but they are random states. It's kind of cloud of atoms. And we look at the excitations of this. Still, we have the same property of the translation invariance, but not in the lattice, but on random. So what is the problem? We cannot use the same property. We do not have the diagonal, which is random. We have just constant energy, which is eigenenergy, and we cannot use this matrix inversion trick. Instead, what we did with my former PhD students, we developed the special renormalization group on that, and you can still find that the same kind of duality is there. So just to summarize this, it will look the same. If I start with really quickly decaying f, like it decays faster than the deep power of the distance, then nothing will change. But if it decays slower, what I will see is that the residual part will depend on the f and the integral of f, the dimensional integral of f up to the same distance squared. So it means that if this f, if I just estimate it like, let it be so slowly decaying that this integral sitting at the upper, at the upper distance, then you see it's just r to the power 2d and f squared that it will cancel one of those. You see the slower decaying this, the faster decays. This is decaying, slowly decaying. So if it decays slower, the closer we're to d. And it's the same kind of the symmetry which we have. If I have the model like that, I can map it to the model. This is more or less a generic thing which you can find. Again, the property of this, like this renormalization group, works as soon as this f is small.
Maybe a stupid question. So this perturbation theory that you developed, this only works for this type of models with long range hopping. Meaning what I'm asking is if I have, let's say, some sort of interaction or like
it works only for single particle.
only for single particle.
Otherwise, so this feature of power law decayed diagonal disorder level spacing is not the same. Exponential. Because the number, like in the Hilbert space, the number of neighbors will grow exponentially, at least. But there you can say, oh, so here I consider single particle power law versus power law. There it will be exponential versus exponential. Short range of the hierarchical lattice, like in Hilbert-space, will decay exponentially, like in usual Anderson, but the number of neighbors will increase exponentially. This is the way how to find a transition of Kelly tree or random regular.
All right. And there, you also have some sort of perturbation theory or not?
Within the localized space, yes. In order to find a transition, you can do it self-consistently, like cavity method, or if you know what the chocolate with Anderson, for settles.
Okay.
Yeah. So I have probably -5 minutes, right? I can jump to the summary if you want, or I can show you what will happen if we add.
You have 10 more minutes.
But it's
1 hour.
45 minutes, no?
Who said that?
1 hour.
1 hour.
1 hour.
Who said that?
Okay, just okay, fine.
10
I have
more.
10 minutes, then I will
At
continue.
least 10 more minutes.
Great. Then I will continue with another one where I can really generalize this Aubry-André duality. So I mentioned to you long range systems where you can have the transition and these correlations can really localize back the system. So, okay, Aubry-André correlations delocalize the system. Here, hopping term, correlations localize the system. So correlations can do many things. So depending on which kind of correlations. Let me consider the models which are self-dual in the same manner as Aubry-André, but which do not use any quasiperiodicity. So what we already know about these power law band matrices, what we already understood is that, okay, it's just the resonance counting, which was there, power law decay, and the hopping term is really uncorrelated random disorder. Therefore, we had this counting, we said, oh, what will be the typical level spacing? It was just the energy window divided by the number of points in this sphere, radius r. Nothing.
So the question, when you mentioned that you did it for a irregular lattice, then you,
Still, I assume
you
that
didn't
density-
have disorder, right? In that
Yeah,
case?
but still I assume that density is more or less.
Okay.
Disorder is at the level of interatomic distances, but if I take the big radius, it's more or less. Of course, if you consider inhomogeneous systems, this is not applicable so straightforwardly, but you should take into account how it will change from a certain point. From the other point, it will be different function, right?
I see. Good.
No. So let's consider correlated diagonal disorder. For simplicity, let me consider translation-invariant because everything looks like after averaging it will be translation-invariant. Let me consider translation-invariant correlations, like homogeneous correlations of diagonals with a certain function. I should really find the way how to calculate this level spacing in order to do this count. To do this, let me do the following. Let me find what will be the expression for this each of this epsilon in the Fourier base. And with this kind of correlations, you can really find that each of these epsilon diagonal disorder will be given by uncorrelated random numbers with a certain variance, which is p-dependent. If it's p-dependent variance, then immediately what you will have all kinds of correlations. And all kinds of correlated functions of this kind can be expressed by the set of uncorrelated random numbers in. This you can show, if you want, I can show it. It's like that. But after that, as soon as it's just the Fourier transform of uncorrelated random numbers with a certain inhomogeneous variance, I immediately can calculate the difference at a certain distance, right? What I should do? First, I will just find what will be the variance at all of them, all R to D levels at a certain distance R. What will be the variance? It's given by random numbers with random phase, with some phases, but random numbers, they also are complex random numbers. Therefore, according to this central limit theorem, it will be Gaussian distributed difference. And the only thing which I should worry about is the variance. I will find the variance. And this variance will be just given by the difference between this project. But you see, this variance depends on the distance now. It means that at distance r, I cannot just count number of them and say, oh, w will be divided by r to d. I should implement w, which is r dependent. But apart from that, everything is fine. I just implement r, wr divided by r to d. In my models, which I consider this w is also dependent on the system size or volume of the system, and it depends differently on the distance, therefore it will be some effective dimension. Apart from that, I can calculate the number of resonances, and now it will depend not only on the distance, but also on this effective disorder, which can be volume dependent. And therefore, I can find the states which are fractal multiprime in this situation. Let me consider the model, because I started with something with the power law, the Hopin term. Let me consider the model where I can find it as self-dual. For this, I will really limit this variance of the effective Hopin terms in the elemental space to be also power law decay with the different parameters, right? And then the larger this parameter, the more correlated elements will be. The smaller number of elements in the sum will contribute to all the diagonal elements, the more correlated will be. But as soon as A prime is equal to this A, it will be self-dual for all the range of A, going from 0, which is analog of Rosenzweig model, but translation invariant now. Sorry, Rosenzweig-Porter, but translation invariant. To A going to infinity, which is just a binary model. Not Aubry-André, unfortunately, because I didn't put anything to it. Okay, so then what I can do, I can find the phase diagram of this model in real elemental space. So elemental space, as I already mentioned, it will be just the same, just these diagonal elements will give me the Hopin terms which decay in the following fashion. And this former Hopin term, now I consider them to be translation invariant but random, will be diagonal terms at random. It's also correlated. Right? And this correlation function will be given by the power law decay of these Hopin terms. Okay, so self-duality is already mentioned. Now I can find the phase diagram, I can count the number of resonances. If number of resonances is finite, so it's written smaller than 1, just finite. So I can find this part. And you see that numerically, what you see is just the fractal dimension, which is close to 0. So it's everywhere here is close to 0. Fine?
Why there is such an angle there on the red curve?
Because so the problem is that as soon as it's the same problem as previously, as soon as my A prime is smaller than 1/2, this series diverge. As soon as this series diverge, it means that the variance of my diagonal will start to scale. Unfortunately, it's the same problem as previously with the divergence of the spectrum. So therefore, I will always have some cusp on the 1/2 of one or the other, depending on which space I consider. In real space, it will get. Yes, so if I would like to consider that I have something like Rosenzweig-Porter, that's what does it mean in terms of resonances? I count the number of resonances as a function of distance. And what I see that, like in this situation, up to some distance, I have resonances and then nothing. For the long range system, I don't have resonances up to some distance and then they start to be there. So it's long range, like it's from the very beginning, long range model. Very similar to Rosenzweig-Porter. In this situation, because some of the Hopin terms, it's A prime smaller than 1/2, then diagonal terms start to scale with the system size, it will be just for the Rosenzweig-Porter. You can find the fractal dimension. So if you have the standard power law random matrix situation, then so for this you should consider the situation that A is probably case larger than the effective dimension. Then what you will see that resonances are up to a certain point R star, and after that they will decay. But this R star will increase with the system size because of our self-duality. So it means that it looks like power law, random matrices in the localized space, but now the head of the wave function, before we have this power law decay, we start to increase this multifractality.
Sorry, what is the color code in the plot?
Color code is fractal dimension. Red is localization, 0 fractal dimension, blue is delocalization. Yellowish, it will be fractal multiple.
So you're plotting the fractal dimension.
Yeah, and the final situation, then what I have is this. This part is multifractality, which is of this kind, which is as soon as the effect is smaller than 1, not only small. I have this multifractality, this R star, it depends in the power law fashion and much smaller than the system size, much larger than 0. No, 0. Yeah, so you can check this by checking the Rosenzweig-Porter like behavior, like that, like as a function of A, it will depend linearly up to some point if you are not very close to the critical point. If you are close to the critical point here, so some other contributions start to contribute here, and then it's not so linear, it will be linear.
And what means negative dimension?
It's just finite side effect, just extrapolation, so that it goes so quickly to 0, which it's extrapolated to functions. Yeah, and here, if I consider this multifractality, it's again, it will be here it's ergodic, and after that it will decay, and then it will saturate. I didn't mention that probably, but at some point, shoot. So at some point, as soon as my D effective becomes smaller than 1, not only smaller than A, but smaller than 1, what I will start to see that 1 defeat should start to, like it will be so short range effectively that I should really take into account the fact that the exponential localization can jump into. It will be independent of localization because my effective is always. So it means it might be delocalized, so ergodic multifractal, whatever, depending on this how this calculation or increase. But this is what you see here at the saturation point. It stops behaving like stops the behavior. So, and of course, because like this is self-dual model or dual model, if I plot the this level spacing ratio, it will be symmetric. So it will show you more or less the same behavior. Like so, here it's ergodic Wigner-Dyson. Here and also in the Rosenzweig-Porter, we know that in fractal phase, R statistics behaves as Wigner-Dyson. In the localized phase, it's Poisson. In this phase, which is nearly 1D Anderson model with the localization and scale with the system size, it will be Poisson, but you see it will be symmetric with respect to the bisector because the same I will see in the momentum. And the same phase diagram is plotted like this dashed lines. It will be there. Yeah, let me just summarize all these two of models which I considered. First, what we can do if we implement some correlations in the Hopin term, we can localize the system. And the main idea there is there's just few, maybe extensive number, but measure 0 of high energy delocalized states, and really split out of this effective disorder from the rest and the bulk. On the other side of the transition, if we implement some correlations in the diagonal disorder, we can generalize this resonance counting just in such a way that we should put here the distance-dependent width. And in such a way, we can find the phase diagram of many models. This model was motivated by generalizing Aubry-André to the cell duality without quasiperiodicity, but okay, you can do it to any other models with some kind of translation-invariant correlations. All this can be used, and my initial idea to start working on that was to use it for the localization of light setups. What is missing here still, what is localization of light? I have the cloud of atoms randomly situated, and I send the light there. And I consider the scattering picture. The effective model there is, with an open quantum system, effective model can be considered as non-hermitistic. So therefore, the question is like how this correlation-induced localization will survive with effective model. This is the question. And yeah, thank you for your attention. If you need these slides, you can just scan this QR code. Thank you very much. Sorry for being late.
So I will start with the function. So when you talk about this phase being multifractal, I would expect calculations for not just D2 but other higher D.
Yeah, so I missed it. Like I didn't put it on the slide. So if you go to the paper, yes, we calculated the infinity.
I see. So
The infinity can be calculated, and you can find that the infinity is different. We checked like a similar plot is there. That work?
I think so, yes. It's going to Dropbox or something.
Yes.
sorry, all these D's should be different, right? For
It's enough to
being
have
called-
just two. Right? So
Yeah, but
the infinity-
these two should be, I mean, the two D's that you calculate must be different for it to be multiple. Yeah, so they are, I mean, what is the kind of difference that you observe?
What do you mean? D infinity is always small or equal than D2. So we
Yeah.
just found that it will be below, always below. Except this part for fractal, but it's just like if you consider exponentially decaying wave function with the length, like with the decay length, which is scaling up with the system size, will be the only. All this is fractal. With process. But apart from that, apart from this saturation part, here it will be here it's still fractal. So it's in this part.
More questions?
So the way that you can derive the duality, because you have the single particle Hamiltonian. Can you think about like many-body and you still can do
This
this?
is what we're doing now. Yes, you can do you can do the same like stuff with interacting terms, which are software as well. But they are like
So what's the duality when you do in the
Fourier
many-body
transform.
question?
It's one kind of duality, another kind of duality which can be there. It can be, for example, if I consider a spin system, it can be, let's say, local transformation Z to X. It's also duality. So it's kind of the duality on the graph.
But that doesn't really get you from something local to something localized. Z to X.
So in terms of real space, it's more. In terms of Hilbert-space dimension, fractal dimension will go from 0 to 1.
So in the interacting problem, you will have the local interaction and
I cannot make it completely local. It will be some spreads, like
Yeah,
Gaussian
some spread,
spreads, and then the same Gaussian spreads or like similar one in the air.
because in your like single breaker model so far, the local it means like tunneling locally,
Yeah.
and you have the tunneling further. Now you have the interaction. You need to have the interaction locally and interaction further, and you will transform.
Yeah. So the easiest way to say that it's Gaussian and the Fourier transform is also Gaussian, and if width is comparable, then it's self-local. Otherwise, one is preferred more local.
But what happens if you have like maybe it's more interesting if you have both interaction and single particle, so you can have different kind of like duality. You can do in the interaction part, and you have to do in the
Sure. So in order to describe many-body localization, and like the idea is the following: this self-dual point, I would like to put the many-body localization point in order to find the nature of this criticality, whatever. For this, of course, I need disorder, hopping term, and interaction. So if I put interaction to be self-dual in one manner, then disorder and hopping term, like in single particle, one will be dual or like with respect to the same Fourier transform, but
Oh, if there are no further questions, let's thank the speaker again.
It's okay. You just announced about dinner.
Yeah, you usually do it.
Oh, you did.
Okay, I will do. So we will have a dinner today somewhere there in the lounge. There should be some food.
Food outside here.
Already? No.
I think already because Berlin sent a message.
Huh?
Berlin sent a message about 1 hour ago.
Before the talk.
So the very cold food.
Maybe, I don't know. We should check. So yes, we have some food outside
here
after seminars.
Yeah.
There is a lunch over there.
It is an analytical continuation from
I see.
I thought.
Okay.